It may oscillate, a different issue. For static stability, those things are not important. For static stability, it's only important that it should have initial tendency to go towards the equilibrium. That is static stability. Now, for this mass spring system, who is providing these static stability characteristics? It is through the spring. The moment I stretch the spring, there is an opposing force which tries to take it back to the equilibrium. Now let us come back to the aircraft. If I say for aircraft, for time being, if we concentrate on the angular stability, that is, suppose the airplane is going like this, and if there is a disturbance which tries to take the attitude up, we have to check it will be statically stable if it has initial tendency to come back to the same equilibrium, okay, or to the equilibrium, that initial tendency. That means for a mass spring system, it has a spring which does all this work. But for an aircraft, what is that agency who will ensure that the moment I am deviating from the equilibrium, there will be a restoring moment which will try to take back it to the equilibrium. That is, if it is going like this, if it is disturbed and its attitude has increased, then the aircraft should have a mechanism which should try to give a nose down moment to ensure that it has static stability. Is it clear? Now the question is for a
Wait. I actually understood. I actually understood what he said. I'm not going to use iPad, but I'm not going to use iPad. I'm going to use the Joplin notes. This will be aerospace engineering. So that there, all those, how do I move them? Move to notebook. Okay, let's create a new book, cybersecurity. I'm gonna move all those to cybersecurity. And so you said, well, now, what is the aircraft? If we concentrate, wait, stop. Where's transcript? 154 to 355. Would it be possible to explain like what is going on? Leave this in full. And let's go here. So would it be possible to explain what is going on here? I'm not going to do window capture. I'm like tired of doing window capture. Let's do. I mean, sorry. Yeah, I'm just going to do display capture. So you're going to see everything. There you go. So pretty much you're going to see everything. what is going on here? And firstly, and how does this correlate to here? One step, one step at a time. So one step, let me understand the next step. And if any programming is required, let's do the programming. Yeah, let's do the programming. Do I have MATLAB? I don't have MATLAB, so I have to install MATLAB. Okay, so if the aircraft gets disturbed, what physically pushes it back towards equilibrium? So for a spring mass system, spring is a restoring mechanism. If it moves away, the spring force pulls it back. So if it goes there, then it's going to make sure that it pulls back. And so negative sign means the displacement to the right means force is to the left, displacement to the left, displacement to the left, force to the right. So if as you squeeze, it'll try to push back. As you pull, it'll try to pull back. Aircraft do not have a giant spring. Aircraft air itself is the spring because it's going to act equal and opposite force. So if there's disturbance upwards, the aircraft will create the restoring force that will force the nose to pinch downwards. So if it's upwards, it's going to make sure it's going to go down. And so that's the negative restoring force. So mathematically, curl A, curl alpha, if it is greater than zero, if that disturbance is greater than zero, meaning if it's going upwards, it must produce some mass. What's M? Oh no, M being the pitching moment must be less than zero. So as it goes up, there must be some pitching moment that should go down so that it stays stable. Makes sense. So curl M by curl alpha must be less than zero. And this is one of the most, okay, I have to write it down. This is lecture 1. So, hmm, okay, wait. Stop using extra English and overlap the core explanation. The only English you are going to have is the core explanation. That's it. So, mass spring system, the displacement is that x is greater than 0. Displacement is that x is greater than 0. And the spring will create the opposite force. F is equal to minus kx. Right? And because there's a negative sign, so it's a spring mass system. If x is greater than 0, force is less than 0. So system will try to return to equilibrium. So the main aim is to return to the equilibrium. And in an aircraft, equilibrium is that the summation of that pitching moment must be equal to 0. The disturbance will increase the angle of attack. The angle of attack being the del alpha, which is greater than 0. And now because the del alpha is actually greater than 0, you must make sure that some pitching moment is less than 0. Like you must have a negative pitch moment in which you are going to force the aircraft to have a stable aircraft, right? So In this case, you're going to have a nose down restoring force. So static stability condition is that curl m by curl alpha must be less than 0. So increase in angle of attack would mean that there will be a restoring negative moment. Now, where does restoring moment come from? So aerodynamic force is F is equal to md. The tail force is F tail, so the force for the tail. The distance from center of gravity is d and produces the restoring torque. Okay. The desired trajectory x of dt, and the disturbance could be the wind or the thrust or thrust error or the density uncertainty. And because of those disturbances, the original displacement, the original trajectory minus the desired trajectory will not be zero. The only reason it is not going to be zero is because you have some wind, you have some thrust, you have some uncertainty, right? You can have anything. Anything is considered an uncertainty here. Holy shit. Holy shit, it actually makes sense. So mass spring system. So you have, initially, if you have like if anything you do, the displacement will always be greater than zero, right? So x is always greater than zero. Oh, come on. X is always greater than zero. This means displacement is always greater than zero. And the restoring force F is equal to minus kx. So x greater than zero, F less than zero. Now, in an aircraft, if you have the equilibrium, so in an aircraft or in any aerospace um, vehicles, so in any aerospace vehicles, you must have that the summation of m must equal to zero, and the disturbance of attack must be if it is greater than zero, if the del alpha is greater than zero, then m must be less than zero. This is your restoring pitching moment. That this is what you call the equilibrium, right? The restoring pitching moment. The restoring pitching moment. This must be less than zero. So it should be a nose down, meaning your curl m by curl alpha will be less than zero. Why? Because your m is less than zero. Right? Because your m is less than zero, the differentiation for any negative value will always be a negative value, right? Unless it's exponential. But here we're not focusing on exponential. This is not exponential yet, right? So obviously, because increase in attack would like increase that restoring negative moment. So keyword is that increase in attack means increase in the negative restoring force. In the negative restoring force. So the aerodynamic force, obviously, the aerodynamic force would be F is equal to md. How many playlists are there? Oh shit, 16. Hmm. We'll see. We'll see what can be done. We'll see what can. My goal is to finish chapter one in 1 week. 1 week or 10 days. At least that's my ultimate plan. So F is equal to md, and so obviously the aerodynamic m is equal to ft. Sorry. So m is equal to fd, and the tail force is f of tail. The distance from the center of gravity is d, and which produces the restoring torque. So the aerodynamic force m is equal to fd. The tail force would be f, the force from the tail, and the distance from center of gravity, distance from center of gravity will be d. And these are like the general concepts, right? For it doesn't have to be rocket specifically, right? It can also be an airplane, but rocket is, so for a rocket example, they will always have what you call trajectory. Even airplane has trajectory, right? So let's say our desired trajectory would be xt of t, let's say, for example, and obviously the disturbances or the uncertainty would be, this is a correlation, right? So the uncertainty would be, let's say, wind or thrust or density uncertainty. It could be anything. Density uncertainty, right? So they can cause deviation. So now you're going to have x of t minus xd of t not equal to 0. X of t being um, the trajectory that has occurred in real life. The trajectory that has occurred in real life. And this is the desired trajectory. All right. So we have our adaptive model. So therefore x dot be f of x, u, p of t, and w of t. Now what is w of t? P of t changes online? You mean P of t changes mid-flight? I don't know, what do you mean change online? Hmm. But I understood what's going on. So this is pretty much step one. There is one.
This is a symmetric aerofoil, and also we know there is a point called aerodynamic center. Aerodynamic
Oh, I hate this.
on the body acting at c by 4. So you'll find that to ensure it has static stability. That is the question we are addressing.
414 to 612. 414 to 612. I use my abstract as an example to explain thoroughly what is going on. Again, you're going more English. Come on, man. Okay, so you said symmetric aerofoil. So lift will be C of L, drag will be C of D, pitching moment will be C of M. So the aerodynamic center is located approximately at x of AC being C by 4, the quarter chord point. The definition is that moment about aerodynamic center does not change with angle of attack. Mathematically, the curl M of what's aerodynamic center by curl alpha will be 0, meaning even if alpha increases, the moment about aerodynamic center will remain constant. Now, aircraft rotates about center of gravity, CG, so center of gravity, not an aerodynamic center. Now, suppose if the aerodynamic center is behind C of G, the lift force acts upwards, and the distance from CG would be d, and so the moment would be m is equal to LD. The disturbance here is increasing. and because the lift angle of attack increases, which means the lift will increase. And since the the lift is increasing, what is CFL again? Yeah, the lift is increasing, then the equation, the half rho v square s CL will also increase. Okay. So the rocket ascending. So rocket ascending. Okay. So wind shear, the thrust will mismatch, the density uncertainty. They're going to cause some disturbance, right? So the change in alpha. The tilt changes airflow. So airflow changes the aerodynamic force. Thus, CFL, CFD, CFM, the lift, the drag, the moment force all changes. Suppose the wind pushes rocket nose upwards. Rocket nose upwards. Then your alpha, which is the disturbance, will also increase, and the aerodynamic load will also increase asymmetrically, which means it's going to create a pitching moment. And if restoring where m is less than 0, the rocket rotates nose down. Can you explain the example again if you don't mind? Can you explain the rocket example again? Also, whenever you are explaining, use only my abstract as an example to explain what is going on. So the rocket is ascending. So the desired trajectory x d of t, that's the desired trajectory. Real trajectory is x of t. Initially, because you know, your there is no disturbance, so the real trajectory is equivalent to the desired trajectory, right? Because nothing's affecting. Then the wind gust will happen, some disturbance will happen, some thrust will happen, some changes will happen. And we said that there are going to be wind shear, there'll be aerodynamic uncertainty, there'll be thrust variation. And suppose wind pushes the rocket nose upwards, which means your disturbance is increasing, meaning the angle of attack is increasing. And the airflow rocket changes, and so which means your lift will change, your drag will change, your pitch moment will change. And because the lift changes, the pitching moment changes. And if nothing corrects it, rocket will deviate more and more. So the error will continue to increase. Okay, you jumped a bit too much, but you know what? So it's not aware that he jumped, but all right. So you must understand what's going on beforehand. Is it real? All right. So the rocket is ascending. Okay. So the ascending, going up. So let's say, for example, rocket is going upward. Now the rocket is going upwards. So the desired trajectory will be xt of t. So that's your desired trajectory. The desired trajectory be xt of t. Real trajectory will be x of t. Initially, because it's going upward, nothing is affecting anything, right? So because it's going upwards with no disturbance, it's going to be that x of t is equal to xd of t. So obviously there is no change. After a few minutes or maybe a few seconds or maybe a few hours, then you're going to see disturbance occurs. Now disturbance occurs. Disturbance occurs. So we're going to have wind shear, we're going to have aerodynamic uncertainty, we're going to have thrust variation, we're going to have wind shear, we're going to have aerodynamic uncertainty, and we are also going to have thrust variation. So meaning curl of alpha is actually greater than 0, right? And if the disturbance increases, the rocket angle of attack will increase. So rocket angle of attack increases. Now airflow around the rocket changes. Airflow around the rocket will change. So airflow around the rocket. Okay, airflow around the rocket changes. Maybe gets heavier. So the aerodynamic coefficients will change. So you're gonna have the lift will increase. I mean, lift will change. It doesn't. It doesn't. We don't know if it's increasing or decreasing, but it is going to change. So the lift will change. The drag will change. The pitching moment will change. Now, because no, we're not going to highlight yet. Now, let's say the airflow moment is increasing or changing. Now, airflow moment changes. The airflow moment on the rocket changes. The rocket oh $15,000. Hmm. Why? So Bangladesh is amongst the 75 countries. Okay, so Bangladesh is amongst the 75 countries. Mm. So typically, I can't travel to US because we're in strict ban. I know mm, my senior had a chance in Carnegie Mellon to do research for computer science, but he got rejected from here because he's Iranian. So he got rejected immediately on the spot. So they had to reject him. Now airflow moment on the rocket will change. So therefore, we have C of L, C of D, C of M. These will also change. So the lift, drag, and more pitching moment will change. And because the lift changes, where lift is half rho v square SCL, the pitching moment will also change. Pitching moment M also changes. So if the more specifically, if the lift changes, meaning if let's say the lift is increasing, right? If the C of L, that's the coefficient for lift is increasing, the lift will increase. And if the lift increases, the pitching moment will also change. So if lift is increasing, the pitching moment will decrease in this case, right? Because if it increases while the lift is increasing, then your trajectory area will increase so much to a point where it's going to, you don't want that to happen, right? So if the lift increases, the moment will decrease, and if the lift decreases, then so let's say for example it's going up, right? It's going up, 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 up. Now obviously it can't go up all the way, because if it keeps going up all the way, the amount of energy that is restored in that rocket is going to finish very quickly, and then it's going to poof. So instead of going up directly, they have to change the angle, they have to change the pitching moment. So instead of going all the way up, it's going to have to go circular, so that it makes it more efficient. So rather than going pushing it against the gravity, they're going to push alongside the gravity, so it's much faster to go around, right? They would always go around rather than just directly go up. You can't directly go up; it's impossible unless you have the world's. You need like every single. You need the world's energy to be able for the rocket to even go straight up. But even that's not a guarantee whether it'll reach or not, right? If nothing corrects it, so what will happen if nothing corrects it? What happens if nothing corrects it? So we're gonna have E of t being x of t. E of t is equal to x of t minus xt of t. This will continue to increase. This will continue to increase. It's going to go up, 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 up. Because the error will increase. Why will the error increase? Because nothing is like there's nothing being done to correct it. Because when the lift is increasing, something should tell the pitch moment, that model, that okay, the lift is increasing, maybe decrease the pitch moment, decrease the angle, so that it can, you know, it is able to, keep going, able to keep moving. But if you have lift increasing and at the same time we have pitch moment increasing, yeah, you're fucked. You're done. Right? So in general, like in today's guidance, the guidance control. So in today's guidance control, your C of L or C of D, C of M, they're all constant, right? They're all constant because they always presume that nothing will change on them. But obviously, everything changes. Even from the beginning, when they thrust, like where they launch the rocket, the minute they launch the rocket, it is going to increase. It is going to increase. I mean, not increase, I mean change. So in reality, the minute rocket launches, the density, velocity, Mach, mass, everything changes. Density, velocity, Mach, mass, everything changes because it's continuous, right? It continuously changes. Changes continuously. CFL, CFD, or CFM. You can have CFL at a specified time, CFL at CFD at a specified time, because at every time step, these lift or drag or moment, these are going to change. The thrust or the mass is going to change over the period of time, right? So now your adaptive model would be CL of t, CD of t, CM of t, T of t, and M of t. So your lift, drag, mass, thrust, and not mass, sorry, the pitch moment and the mass changes. Wow. So now the MPC will receive the estimated state. Okay, what's going on here? The sensors measure the angle, the velocity, the acceleration, but noisy. So Kalman filter will estimate the true state. All right, I got it. Do they speak about Kalman filter here? I don't think they speak about Kalman filter here, right? Okay, shit. 6:17 to 8:55. Um, 1 minute, 1 minute, 1 minute. You also explained about Kalman filtering. Do we have to know Kalman filtering right now? Because I know that there is a specific lecture specifically for Kalman filtering. Oh, sorry, my bad. There is a specific lecture specifically for Kalman filtering. So do you have like right now, like thoroughly? Hmm. All right, makes sense. All right, so can you use my example and explain what is going on thoroughly? Use my example, please. Use my example and explain it and explain what is going on. I mean, use my abstract, sorry. Use my abstract. I want to see Valentina posted. I mean, yes. Yeah, I can't post as much because still in shadow band. Holy shit. He has good amount of views, my god. Oh my god, man. Yeah, they're nice people, man. They're not nice people. Rocket, okay, so alpha is alpha conjugate, meaning rocket is following desired ascent path correctly. Now, disturbance occurs from your abstract. So, wind shear, the thrust uncertainty, the aerodynamic uncertainty. Suppose the wind gust pushes the nose rocket upwards. So, alpha is alpha conjugate. What is alpha conjugate though? Alpha conjugate is desired, alpha is the real. So, let's say, let's presume alpha is the real trajectory and alpha conjugate is the so alpha is the real trajectory, alpha conjugate is the the desired trajectory, desired trajectory. So meaning the rocket is following the rocket is following a real trajectory, like the rocket is following a desired trajectory. Cool. So rocket meaning ascent, not sorry, not trajectory, ascent. The rocket is following a desired ascent correctly. The disturbance occurs from your abstract. So obviously there's going to be disturbance. There's going to be wind shear. There's going to be thrust uncertainty. There's going to be aerodynamic uncertainty, right? So you're going to have wind shear, have thrust uncertainty. You're going to have aerodynamic uncertainty. You know what's fun? You know what's really fun? I love Valentina, but I don't have to stay updated on what she does. I don't, because I know my objective now. I did that. Like always going to X and then comment. No, I'm not doing that anymore. No more. I love her. That's why I can't, involve myself with what she's doing. Close this. It's cold. Like I can't involve myself with what she's doing. She's doing it because she has her own personal opinions. She knows that, you know, I have to study. She knows that I have to work hard. She knows that I have an objective. I can't lose my objective because I love her. That's why I can't lose my objective. Because I don't even reply to anything now. Because all those people that are commenting, they have no life. They genuinely have no life. I mean, I know she loves someone else, but either or, like, you must come to your senses that these people don't have a life. These people are easily fooled. If she hates, she hates. Because I love her not because of religion. I don't give a shit. Dude, I have other things to worry about, right? Like, why should I love her? That's it. Just because I'm a Muslim doesn't mean I cannot love her. So now, because the disturbance increases, now this means the rocket disturbance increases. Rocket disturbance increases. And so now the rocket will follow a desired path correctly. Oh, wait. No, the rocket will not. This time it is going to increase because you have wind shear, you have thrust, you have all those uncertainties that's playing a role. And it's like, oh. Now you have all the existing uncertainties playing a role. So now you're going to have alpha being alpha conjugate plus the disturbance. So this is no longer at equilibrium. And so due to the increased angle of attack, the lift coefficient changes. So because there's an increase in angle of attack, the lift coefficient will change. So there will be curl C. Okay, how far are we? Oh my god. Yeah, we need to finish quickly. So due to increased angle of attack, so because now there is an increase in angle of attack, so due to increased angle of attack, curl C of L will change, meaning this will actually increase, right? So therefore L is equal to half rho V square SCL. Instead of L, we're going to have del L now. Half rho V square S del CL. Sorry, del CL. Everything else remains constant. The C of L, the lift coefficient will change. Because the lift coefficient will change, the lift must change. And we're continuously monitoring this. Continuously, we're monitoring this. So we're continuously monitoring the lift coefficient, the drag coefficient, the moment coefficient, the thrust, the mass of the rocket. This is continuously being monitored rather than being fixed. This is continuously monitored. 624, 852. Didn't we do that just now? 9, 10, 12, 12. So 906, 12, 12. Same. Use the abstract as example and explanation, like explain the core general concepts, what is going on and stuff. Oh, cool. It's going to rain today. I'm going to go for a walk. I will go for a walk. Definitely, I will go for a walk. Okay, it is raining in. See, if. Where is this end? See, if, let's say, if Valentina were to go, where's Texas? Holy, what is this? No, I know this is Canada. Obviously, I know this is Canada. I can literally see the squares and shit. But where is US? What the fuck is this? Oh my god, there's lightning. Where lightning? Where? Oh, okay. So where's Texas? Like you can already see, like it is. Where's Texas? Where's Tech? God damn it! Where's Texas, man? I know she's here. No, she's not. Is she in Florida? No, she's not in Florida. There, look. The only option you have is go from there. You have to go from there. But if you go straight, that's Africa. But if you go from there, you'd eventually, if she takes the boat, I will eventually see her because I can literally see Europe from here. Just for information, I can see Europe from here. I saw Ireland. Yeah, when I went to Cape Spear, I saw Ireland. So you definitely, I'm definitely going to see you. Man, I'm going to say that. I am going to fucking say that. I don't give a shit. If you ever take a boat, you have to go through Atlantic Ocean. I can see you either or. I can see you from my home because it's not far. Wait, my home is not far from Atlantic Ocean, right? Is it? Wait, where is it? Where is it? Dude, where is it? Come on. Wait, my home is not far from Atlantic Ocean. Hell yeah, my home is right. Yeah, my home is in the Atlantic Ocean. You have to cross St. John's. You have to. Wait, am I right? Yeah, because look where is St. John's? What's that? What the fuck is that? So I live like somewhere here. Look at it. You see, I can literally, and that's what France, Madrid. You have to cross St. John's. You have to go through St. John's. You have to. You have to. You have to cross St. John's. I can see Ireland from my home. No, I know, I know, I know. Like from St. John's to Ireland will only take 4 days by boat. Only 4 days. 3.5 to 4 days. She has to cross St. John's, right? She has to cross St. John's. It doesn't matter. I can still see her. It does not matter. Because, sure, like you can go all the way from there and then. take this middle cut. Yeah, I can still see her. I can still see her. Easy. I can, dude. Like the ocean. This ocean is literally beside where I live. Literally beside where I live. It's like a 5 minute drive. Oh, that'll be sick. She has to cross St. John's. There's no choice. She has to cross St. John's. Wait, wait. Yeah. Now I'm gonna delete them. It's like a 5 minute drive. It's not far. It is not far at all. It's literally right here. Like I can go to the hill. Like I have to go up the hill, and then all the way to the top. Then there's city called Cape Spears, literally above us, like, by hill. I can go there and I can literally see Ireland. Like if you go at daytime or like afternoon, you can see like Ireland. It's not. It's obviously very far, but literally where you stand, and if you have a boat or keep swimming, you'll reach Ireland. It's not far. Ireland is not far from my home. Ireland is not far from my home. Just saying. Ireland is not far from my home. I mean, you have to take a boat, obviously. It's going to take like 3 days, 3.5 days, or 4 days. Yeah, she has to cross St. John's. Either or, we can see her. I told her it's much easier to come to St. John's, and then from there you could go to UK directly. You can do that because by boat it takes like 4 days. So rocket in abstract initially flying correctly. So alpha will be alpha conjugate. So your trajectory will be x of t being x d of t. No, I'm not going to see that. I don't want to put too much pressure on her. I understand what it's like being too much pressurized. Don't want to do that. So in your abstract, in my abstract, I'm going to have that the disturbance initially alpha is alpha conjugate, and which means x of t is the same as x t of t. So there is no disturbance because I mean you're literally ascending, right? At the beginning, there is no wind uncertainty, there is no thrust uncertainty, there's no disturbance uncertainty or whatever. At the beginning, there is no wind uncertainty or thrust uncertainty or any trajectory change uncertainty or trajectory change uncertainty. And let's say initially, now what happens now? Let's say del alpha is 0.5 degrees, right? Now because del alpha is 0.5 degrees, so which means I'm going to have alpha being alpha conjugate plus 0.5. So now it's going to tilt upwards. It's going to tilt upwards, right? Meaning this will tilt upwards. And because now there's an increase in attack, now because obviously there's tilting upwards, increase in attack doesn't mean it's literally being attacked. Increase in attack means because it's changing, it's going upward, right? It's going to tilt upwards. You don't want it to tilt upwards. Now because it is being tilted upwards, the lift coefficient will change. So now you're gonna have this of this. The lift coefficient will change. Lift coefficient changes. Thus, the lift will also change. Lift also changes. Suppose AC, the aerodynamic center, is behind the center of gravity, is going to easily pull. If it's there, it's like a swing. Okay, if I have a rocket, and if my aerodynamic center is here, and this is my center of gravity, it can easily pull downwards. And if my aerodynamic center is here and my center of gravity is here, it's going to push upward. It's like a swing. And so here you're going to have del m less than 0. You're going to have here del m greater than 0. Now if curl alpha is greater than 0 but curl m is also greater than 0, the disturbance will increase severely. And if vice versa, if I have del alpha being less than 0 and del m being less than 0, the alpha will decrease severely. This is why when a plane crashes, let's say it loses one of its wings, it is going to dive down so rapidly because not only your disturbance has increased, but your moment has increased too, to a point where your disturbance is acting opposite, right? Is acting opposite. But now, because let's say, for example, if the pitch moment is going down, because your disturbance will increase either or, right? But this time, yeah, right, your wind disturbance will increase either or, but it's not going down because it doesn't have that stability to be able to keep that plane float right. But because it doesn't have the stability, it's going to pitch down rapidly to a point where it's going to go pew. Because now del alpha greater than 0, wind disturbance increases but towards the opposite side. You must understand that wind disturbance goes from here, right? From the left. Now you don't have a stability. It is literally going to act on the opposite side. It's not going to, stop that because it cannot. It doesn't have the wing or it doesn't have the thrust to be able to stop that. And now on top of that, your pitching moment will also be less than 0. So it's going to go literally bank and then crash. Right? So it's very dangerous. Very, like, you must understand what's going on. So if CG minus AC, if CG is greater than AC, then it's going to pitch upwards. Okay. So if CG minus AC, if CG minus AC greater than 0, then stronger aerodynamic moment. Stronger aerodynamic moment. And if CG less than minus AC is less than 0, weaker aerodynamic moment. Aerodynamic moment. 1522 to 18. To all the way to 18. Again, use the abstract. You see, when they say so you can be an illegal immigrant in the US and England, she's not an illegal immigrant though. She's a legal immigrant. Her father was really good. Like they worked to come here. Like even she herself is very successful. I wish I could reply. I really wish I could reply. I can't reply sadly because this stupid shadow ban. I'm still shadow banned. Yeah, it's going to rain here pretty soon. So rocket ascending under disturbances, the wind shear, aerodynamic uncertainty, thrust uncertainty, the rocket experiences GERD alpha. So there will be a small angular deviation. All right. And the professor now explains not all aerodynamic parts stabilize the vehicle. So some parts stabilize, some destabilize. And it depends on the net moment. Okay, okay, wait. You know what I want to do is like I'm gonna do a live where I literally reply to Valentina's comments by speaking. I am going to do that actually. I am going to do that. Um okay. Explain only using my abstract. The only English I must see is the core I understood. I understood. Don't worry. again. Okay, so alpha is equal to alpha conjugate, and the trajectory is the desired trajectory is equivalent to the real trajectory. On the disturbance from abstract, you have wind shear, you have thrust uncertainty, you have aerodynamic uncertainty, which causes curl alpha to be greater than zero. The rocket body produces destabilizing moment. So curl M of body is greater than zero, meaning the nose up tendency, the trajectory the nose up tendency, there will be a pitch up tendency. The trajectory deviation will increase. The rocket tail or fins produce the restoring moment, where the pitching moment for tail will be less than zero. Because if the body goes up, tail will go down, definitely. So the total aerodynamic moment would be the curl, the del M of body plus del M of tail. Stable case, if the del M of tail is greater than body, then the total will be less than zero. So it'll be almost returned to the alpha conjugate. Unstable is that if body is greater than tail. If body is less than tail, so if it's like this way, little bit this way, then it's easier to do the pitch moment and whatever, because tail has those wings that are adjustable. So you can do that. So it can, easily reach because the total gets less than zero. So it is really easier to, reach towards that equilibrium point. But the unstable is if the body is greater than zero, meaning if it's pitching up, then the pitching total will be greater than zero. The rocket will deviate further. The rocket in an abstract ascending at equilibrium. So we have alpha is equal to alpha conjugate. So rocket abstract equilibrium. So alpha is equal to alpha conjugate. And the trajectory is that x of t is equal to xd of t. The trajectory is that x of t is equal to xd of t. Xd of t. Then disturbance from abstract. So you're going to have you know, the wind shear. You're going to have the thrust uncertainty. Then you're going to have the aerodynamic uncertainty. Aerodynamic uncertainty, which causes that curl alpha to be greater than zero. Now, the destabilizing moment happens, the destabilizing moment occurs. The destabilizing moment occurs when curl M of body is greater than zero, meaning you're going to have a nose up tendency and the trajectory deviation increases, meaning nose up tendency and the trajectory body increases. Body increases. But for this del M of body, being greater than 0, then del m of tail must be less than 0 in order to stabilize it. Now, in order to stabilize it, then your del m of tail must be less than 0. Case 1, if del m of body minus del m of tail is less than 0, meaning tail is greater than body, then it is stable and is very easy for the rocket to reach the equilibrium point. And it is very easy for the rocket to reach equilibrium point. And if del m of body minus del m of tail is greater than 0, so unstable. And vice versa of what less than 0 means. The only way to prevent this is by having, if we have if the distance of tail is greater than 0, if the distance of tail increases, the pitch moment for tail will increase. It's easier for it to pitch upwards. All right. I think we're pretty much done from here. How far are we? Just going to stop for some time.